All right. Next up is William Bowman talking about type closure conversion for the calculus of constructions.
All right, so is this mic working? Okay. So, good afternoon, everyone. It's late. Saving the best for last. Last section of the conference. Second to last talk. But don't worry, I've got a nice, easy talk for you about compilers. Well, proven correct compilers. Well, proven correct compilers that preserve proofs of correctness automatically through compilation. And the axioms of type theory. So let's get started. First, let me deconstruct my title. So I'm working with the calculus of constructions. For those that don't know, this is the core language on which the Coq proof assistant is built. So Coq is a proof assistant based on dependent types. So let's start with dependent types and high assurance software. So here, just to name a few, are some projects written and proven correct in Coq. There are projects like CompCert, a C to x86 compiler written and proven correct in Coq. There's the Certicos project, an operating system kernel with full functional correctness specifications modeled in Coq, proven equivalent to its underlying C and assembly implementations. We have language semantics, things like Vellum, a subset of LLVM formalized in Coq, with the Rust Belt project, semantics of Rust with a program logic for proving safety of unsafe Rust code. On and on, we have lots of these projects. So the way software development works in Coq is you will write down your correctness and safety and security specifications all in the type system. The types are rich enough that you can write down theorems about your programs. And then you write your program. And if it's well typed, then your program is proven correct. So this is great. We have lots of verified code, verified in Coq. But that is not the end of the story. After you verify your program, you probably want to execute it. And so after verifying in Coq, you will typically extract it, that is, compile the program to OCaml, and then the OCaml compiler will take over down to assembly. And now, at each stage of compilation, we have some opportunities to introduce bugs and undo all of our verification effort. So you might think, we should prove these compilers correct. And that is what projects like the Certicos project are doing. The idea is we want to verify each step of compilation, and then we know that the program we end up running is verified to be the program we wrote and verified. And this is great. This is a great idea. But compiler correctness is not the whole story. Correctness is the whole program story, because compiler correctness relies on a closed world assumption that you are not linking with anything. And I have bad news. No one writes whole programs. So yes, we need compiler correctness, but it's not enough, because near enough to every program will be verified, then compiled, and linked with some unverified code. And just like compilation can undo our verification, linking can undo our verification efforts. So every time we compile and link with something, and by the time we get back down to assembly, we'll have linked with the language runtime, the operating system, low-level C libraries, all of these opportunities to undo our verification effort. And this is not a hypothetical example. I have on this machine a Coq program verified to be free of memory errors, and so I eliminate all my bounds checks, and I link with one line of unverified code, and it promptly jumps to an arbitrary location in memory. And the state of the art in avoiding this sort of error is telling the programmer to be careful. So we've gone through all this verification effort, all of our static checking, just to tell ourselves we're smart enough to figure this out. I say no, don't be careful. Use types. Use the types we've been using all along. Don't only verify the compiler, but preserve your types through the compiler until link time. And then at link time, you can use types to enforce invariance through type checking. So ideally, we want to go down to a dependently typed assembly language, at which time we can link. Now we do have a whole program. We can use traditional compiler correctness to go all the way down to machine code. So in particular in this work, we're going to look at type-preserving closure conversion. So closure conversion, standard compiler pass used in functional languages like Coq. So our goal is to write a type-preserving closure conversion translation that preserves dependent types. So to understand type preservation, let's take a brief look at the history of type preservation. So type preservation was introduced in the seminal paper System F to Typed Assembly Language, 1998, and it lays out the minimal core compiler we need to get down from a core calculus to a typed assembly language. First, we do CPS translation. This makes control flow explicit. Then we do closure conversion. This takes first-class functions, turns them into something we can heap allocate. Then we do heap allocation. We make pointers and memory explicit. Then we can do code generation. Now, so for type preserving compilation, for each one of these passes, what we want to do is prove this theorem, which says if E is a well-typed program at type A in our source language, then E plus, the translation of E, should have type A plus, the translation of A. So to do this, to prove this theorem for each of these passes, we need to design a typed intermediate language for each stage of compilation. So a CPS intermediate language with types, a closure converted one, and on and on. And we will want to prove some meta theory. We'll want to prove soundness of this typed intermediate language. So we know that type checking means something. We want to prove decidability. So we know that we can actually type check terms at link time and get an answer. Now, when we move to dependent types, we have new challenges in this design phase. What we're doing is we're trying to design typed languages that can prove theorems. And we're going from type systems that have been designed for functional, compositional programs to type systems that have to reason about global, stateful, instruction-based programs. And when we prove soundness of this system, well, our type system can express theorems, can express set theory. So we have to prove soundness of something that's equivalent to set theory, which means we have to be very careful about which axioms we add to these type systems. Now, just to give you an idea of how hard this is, we'll take a look at the first pass, CPS. In 2002, type-preserving CPS for dependent types was proven impossible. And it remained impossible until very recently, sort of. So this recent result tells us, well, basically, past work doesn't scale in an obvious way to dependent type theory. So actually, the 2002 impossibility result still holds. It says that past proven type-preserving compilers don't scale. If you use translations that worked before, they will not work. The 2018 result tells us, well, if we do something non-standard, we modify the type system, we modify the translation, then we can recover type preservation. But the past work isn't scaling. In this work, we're going to talk about closure conversion. And the key insight is the reason past translation don't scale is because we need to understand which axioms of the type theory past translations rely on, and we need to understand whether those are compatible with dependent type theory. Okay, so let's take a look. In order to understand where the axioms lie, let's take a look at the standard non-dependent type-preserving closure conversion. So our goal is we have this function, f, which takes one argument of type A, returns a result of type B, and in the definition of the function f, we can refer to any variables in scope at the moment. Those are in gamma. And the idea is, since f is a first-class function, when we pass it around as a value, it should have all references to variables in gamma should take on the values they would have taken on in this definition, at this definition site, even when we're passing the function around. So our goal is to translate f into an explicit closure. This is a pair of all of the data, all of the free variables in gamma, and a closed code pointer. And it's going to have some closure type that says, well, it's a closure, but it still takes an argument A and returns a result B. But now it better be the case that the closed code pointer is well typed in an empty environment. So we know that we can take f, lift it out of where it was defined, put it in the heap. So that's our goal. So we can think of this closure as an object that has one method, and gamma is all of the private fields for that object. Okay, so now how do we implement this typed closure? We need some implementation of this closure type and some way to implement this pair. And I'll give you a hint. Well, we can't implement it as pairs. I know operationally I just described it as a pair. It's a pair of some data and a code pointer. But if we try to implement this closure type as a pair of something describing gamma and a code pointer that expects gamma, expects an argument, returns B, we could maybe operationally implement apply as project out the code pointer, apply it to the data, apply it to the argument X. But if we do this, type preservation will fail. So just to see why, we can look at this example where we have two functions, f and f prime, of the same type, nat, arrow, nat. But f, in its definition, refers to some free variable z, and f prime is already closed. Now in the source, these functions have the same type, so we can use them in the same way. We can use them in arbitrary contexts that expect a nat, arrow, nat. But after translation, we've changed the types, and we've introduced, so now our types are not functions, but they're pairs of some environment and some modified function pointer type. But now our types express that, well, f depends on some variable z in its environment, whereas f prime has an empty environment. And now the types are no longer equal. So we've taken these two objects that have the same interface and turned them into things with different interfaces. So and while operationally this may seem like, well, if it works, who cares about type preservation? But by breaking type preservation, we learned that we've violated some invariant. And in particular, this tells us that we've violated the data hiding properties of closures. So actually, in the target language, we've introduced new attacks that were inexpressible. We can just extract all of the hidden data and hand it to any attacker. Okay, so we can't implement closures as pairs. So what can we do? Well, there's been 20 years of work on type preservation, and it tells us we use existential pairs. So we'll still use pairs, but we'll introduce an existential quantification that hides the type of the environment in the type system. And then in the implementation of apply, we'll project out the code, project out the environment, apply the code to the environment. But it will be in the scope of this unpack that ensures that we use anything of type alpha in a particular way. Now, when we look at our example, this existential quantification has hidden the type of the environment in the type system, so f and f prime still have the same type, despite the fact that their environments are different. And if we look at security, the security attack I mentioned earlier is actually not definable. So we can never, we know from type preservation that this closure type has not introduced any additional interfaces. Okay, so 20 years of work, we implement the closure type using existential types. What about dependently typed functions? So here we have another function, takes one argument, x of type A, returns some result of type B. It can refer to all the lexical variables, but we're in a dependently typed language, so can all the types. Types can refer to or depend on terms, including all of the free variables. And actually, the result type B can refer to the argument to this function by the name x. This is what gives us the ability to write down theorems and proofs in our language. So just to give you a sort of intuition about how we can do that, we can statically rule out all division by zero errors by giving division this type, which says division takes two numbers, x and y, and a proof that y is not equal to 0. And this is not some logical representation of y and 0. This is the actual runtime 0, the actual runtime reference to y. So these are terms inside of our type system. Okay, so now we have this dependently typed function. Our goal is to translate it into a closure, a pair of the data and the code pointer. Now we have a dependent closure type. So the closure expects some argument A, returns a result B. B can depend on the argument by the name x. And our code pointer f is still closed. We can allocate it in the heap, but its type is complicated and has all this dependency. So how do we implement the dependently typed closure? Well, I'll give you a hint. Not as pairs. Pairs still don't work. But it turns out neither do existential pairs. And to understand why, you need to understand what it means to say that something exists. So let me digress for a moment and talk about philosophy. No, okay, so I said that the key to understanding this problem is understanding the axioms that past work rely on. And when I say axioms here, I'm talking about axioms in type theory. So they actually have computational content. From a programming language's perspective, you can think of axiom as primitive, but I'm focusing on logical consistency here, so I'm thinking about this typing rule as an axiom. So the question is, can we use this axiom, which all past closure conversion translations, except one, use? Well, let's see what this axiom says. This axiom says that if A is a type, under the assumption that alpha is a type, then there exists an alpha such that A holds of alpha is a type. Now, it may not be immediately apparent, but this axiom has some very interesting properties. So the first one, existence, this existential type, is impredicative. Now, I don't know if you've heard about impredicativity recently, but it has some interesting features, which will come up in a moment. But it basically means that this type is formed by quantifying over other types, including itself. So if you imagine types as sets, alpha is a set, so we're quantifying over sets that include the type we are constructing now. Now, the reason we need this is easy to see if you consider recursive closures, so closures whose environment contain a reference to the code pointer we're constructing now. And this is fine to do as long as your recursive closure is inductively well-defined, but it is a bit scary. Okay, so the second property is that anything of this type ought to be computationally relevant. So what we're doing here is compiling programs, which we intend to run at runtime. So the components of this existential pair, like the code pointer and the data, ought to exist when we try to run our program. Okay, all past work also relies on a parametric interpretation of this rule, which says not only are we polymorphic in alpha, we are parametric in alpha. You cannot inspect the type of alpha at runtime. If you do, then you can break certain security guarantees. And finally, we need to use this sort of type in large elimination, which just means that when we can actually compute types from terms. So we can do things like say, if x, then nat, else bool. So we can actually eliminate runtime terms to compute types. Now, since we're compiling dependent functions into this existential type, this closure, we need, and dependent functions can be used with large elimination. We also need whatever our closure type is to support large elimination. Okay, so these are the properties we need. And actually, we could add this axiom to the calculus of constructions. In theory, that would be fine. But in reality, in practice, this type is not compatible with real proof assistance. So the first one is impredicativity. You might have noticed recently that most real compilers don't allow impredicativity. And in particular, Agda and Coq don't allow this. So Coq actually allows it in a non-computationally relevant universe, or you can add a flag that will make your types inconsistent with certain other interpretations, so you can sort of get it. But in practice, you can't really rely on impredicativity. We also can't rely on parametricity. Most type theories, well, some type theories don't admit parametricity. Most of them don't admit it by default. And in particular, Coq and Agda don't admit it. And, well, you can get it in Coq by downloading a plugin and doing a translation. It's a whole thing. But then you'll be inconsistent with certain other things. And finally, and most importantly, this axiom is incompatible with set theory. And some people do use set theoretic reasoning when doing proofs. So for instance, if you want impredicativity, large elimination, and excluded middle, you can't have that, implies false. If you want impredicativity, relevance, and excluded middle, can't have that either, implies false. So we cannot use this axiom in real dependently typed languages. So what can we do? Can't use pairs, can't use existential pairs. How do we implement our dependently typed closure? Well, I'm going to do it using closures. So essentially what we'll do is axiomatize our type theory with closures. We will add a closure primitive. Now, this has some downsides. For one, we've added a new axiom to our system, so we have to prove consistency. We can't rely on the consistency of well-known types. For two, it's unclear how past work, all 20 years of this past work that uses existential types, scales. For instance, how do we do optimizations for typed recursive closures? That all relies on existential types. But it has the benefit of working. So, here are my closure axioms. First one tells us when a well-typed code pointer is well-typed, when a code pointer is well-typed. So this says that we have a code pointer pointing to E, which expects two arguments, some data n and some argument x, where n has type A prime and x has type A. And it has this dependent code type, which says that, well, this is a code pointer and it expects an n of type A prime and x of type A, where A can depend on n, and the result type is B, and B can depend on n and x. So this is well-typed when E is a block of code that produces a B, and it only refers to n and x. Notice that we've dropped gamma. So E has to be well-typed in an empty environment, except for its formal parameters. Okay, so that's code pointers, and this is the closure. A closure has a code pointer E and some data E prime, and their types line up. And the type of a closure has the type pi. It expects an argument x of type A, where we've, for dependency reasons, replaced all references to the data argument n by the actual data E prime, and it produces some type B with all references to n replaced by the actual data of the closures E prime. So these are the two rules, and they may appear deceptively simple, and there's two more that you can find in the paper, and there's an equivalence between closures for deciding equivalence. Now we have to show these axioms are compatible with type theory in general. So that's what we do. We prove logical consistency of our target language, and our proof is orthogonal to all the things that we don't want. So it does not rely on impredicativity. It doesn't rely on relevance or parametricity or large elimination or set theory. We also prove type safety. So in this intermediate language, you know any well-typed program is type and memory safe. This means we can actually validate the output of our compiler to a certain degree just by type checking. And if you have a full functional correctness specification in your source, well, that's preserved. So you can actually do certifying compilation when you have the full spec. And we can enforce safe linking just by type checking at link time. OK, now let me briefly show you the closure conversion translation. It's actually not very interesting once we've designed the target language to handle it. So what we're going to do is translate pi types, which describe functions or implicit closures in the source, to pi types, which describe explicit closures in the target language. We're going to translate first-class functions into explicit closures, where we have a pair of some scary code that I'll show you in a second, and all of the free variables defined in an explicit data structure. So this part, totally standard. Now we introduce our code pointer, and we say, well, the code pointer expects some data, n, some argument, x, and then we're going to project all the free variables out of the data in the scope of our code E. Totally standard. Now what's not standard is what we have to do for dependent types. So we actually have to bind all of the free variables in the type annotation on x. Because we have dependent types, this type annotation A can refer to free variables. So in our translation of this code, we have to project all of the free variables xi from n in the type annotation. And similarly, in the type annotation for the data part, describing all of the free variables, we have to use a dependent type that binds each free variable in the type of the next free variable. So this sigma type is essentially a dependent list. All right, so that's the essence of our translation. Now, we prove type preservation. There's not much to say about the proof. It's not very interesting. As I mentioned in the beginning, this is not really a replacement for correctness. So we also prove correctness of separate compilation. So if we have some component E linked with some components gamma in the source, and we link them and run them to a value in the source semantics, we can separately compile E, separately compile gamma, link them in the target, and we'll give an equivalent value running it in the target language. All right, I'll just say a few things about future work. Future work, this is the calculus of constructions, but Coq actually uses the calculus of inductive constructions. So we need to scale to recursion, which we should be able to do because we spent a lot of time designing this to do that. Should be able to scale to the universe hierarchy since we don't rely on impredicativity. There are a few more challenges down the pipeline. Basically, the lesson here is that, well, past work relies on axioms that no longer hold. And in particular, past work for allocation relies on linear types, which don't play well with dependent types. OK, so in conclusion, typed closure conversion of the calculus of constructions. We have to abandon all the past work on type preservation, in particular existential types, to make this work. And in general, this lesson applies to lots of the type preserving translations, like CPS, like allocation. Thank you.
Questions?
I'm Stephen Dillon, the University of Cambridge. I have two questions. The first was, when you said it's orthogonal to the impredicativity and large elimination and so on, I'm wondering exactly what that means. I get that you're not depending on those, but do you remain consistent with those in the same way that normal calculus of construction is?
Yeah, so technically speaking, that's what I mean. We don't rely on them, and it is still consistent with all of those features.
Oh, great.
Yes.
And the second thing I was wondering is the code types describe essentially a thing that can only be produced in the empty context, and seem remarkably like the boxes in various modal logics.
Yes. So I have a colleague who's working on this. Closure conversion is essentially is well described by a modal logic where you have two kinds of variables: global variables and lexical variables. So I haven't done this in a modal way, but we should definitely talk offline because that's true. This is very modal.
Okay,
thank you.
Please.
I'm Nini from the University of Hong Kong. So I'm wondering what's the type of code?
Yes, so this is one of the axioms I didn't show. So code itself has a type, and its type is very much like pi types in Coq. So if you have an impredicative universe, code has to be impredicative as well, or have an impredicative rule as well. Otherwise, code has the type type. So essentially, code has the type, but
Okay.
the premises depend on your impredicativity rules. So in the paper, we give both an impredicative version of code and a predicative version of code.
Okay. Will it cause any problem if you want to create the closure of a program which itself includes a closure? Because you can have closure in the expression level, right?
Right. So I haven't looked at doing recursive closures yet, but a lot of the work was explicitly to support induction. So I think that this should work, but I'm not totally sure whether or not it depends on impredicativity yet. My hope is it doesn't.
Okay. Thank you.
Yeah.
All right, we're out of time, so let's thank William.